Hello everyone. In this video, we will discuss the fundamentals of electric drives. So basically, why I use the word fundamentals? Because electric drives is a very vast concept. So in the BTech level, we will have a very basic introduction of these electric drives. Okay. Now, first in this first few minutes, we will discuss what is a basic definition of a drive and what is the basic purpose of an electric drive. Okay. So, if you see the definition, electric drive, or first let us define a drive. Basically, a drive is a system used for or used to control the motion of an object. The motion of an object. Okay. Say for example, let us say there is an object, motor shaft. We would like to change its let us say position or a speed. Basically, these are the two things that we are going to control. So, in any particular system, if you change the position of an object or change the speed of an object in a controlled manner, that is called a drive. And if an electric motor is used for this purpose, if an electric motor is used for this purpose, then it is called electric drive. If an electric motor is used for this purpose, then it is called an electric drive. Okay. So basically, electric drive is a system which is used to change the physical motion of an object. That physical motion can be either position or speed of a certain object. Okay. So if you look into any electric drive, it will have three major components. One is electric motor, another is control system, and energy transmitting circuit or transmitting system. So basically, in this topic, we will mainly discuss about this one, energy transmitting system, that is basically a power electronic converter. Okay. Now, before moving to this one, let us go to what is the basic purpose of an electric drive. So why the drives are important and what is the role of power electronic circuits in these particular drive applications. Let us discuss this concept with an example. Now let us discuss what is the role of power electronic circuits in electric drives. If you remember, I might discuss about this topic in the introduction of power electronics course. However, let us relook into for the benefit of recollection. See here, this is a pump example. Let us say this is a pump. Pump application, normally every household will have it. So what is the basic purpose of a pump? To take water from ground level, let me call it inlet position, to take water from ground level at inlet position and to control the flow of this water at outlet position. So for that purpose, this pump is driven by an electric motor, where this motor is supplied from utility system. What do you mean by utility system? Our normal distribution system, either single phase or three phase, depends on the power rating of the electric motor, and normally frequency is a local grid frequency. In our country the frequency is 50 hertz, nothing wrong if you even if you take 60 hertz supply also. But the point is, the motor will be driven at constant speed. The motor will be driven at constant, you can also say it is at fixed speed. Now the question is, when the motor is operating with a fixed speed, how can we control the flow at outlet position? So for that, there is a mechanical system. This is called throttle valve. By using this valve position, by adjusting the valve position either completely closed or completely open, we can adjust the flow of outlet. So what we can understand from this, let me call it system 1. In this system 1, irrespective of the flow at the outlet, as the motor is driving at constant speed, it will take always same power from utility system. Therefore, what do you mean by that? Whether you are using at output or not, as a motor is running always at same speed, it is consuming same power from the utility system. This is one aspect, okay, the very traditional way of pump application. Now the same objective will try to achieve with a slight modification in the second system, okay, in the second system, let me call it system 2. Here also objective is the same. What is that? We will take the water from ground levels at inlet position, and there is a pump, let me call it with P, P stands for pump, and we need to control the flow of water at this outlet position, okay. Now for this, if you observe carefully, in the second system the throttle valve is removed. When the valve is removed, the question is, how can we control the flow of water at outlet position, okay. Now follow carefully here. The concept is, in this case also the pump is driven by electric motor. The pump is driven by electric motor, where electric motor is connected from utility system. But this motor, follow carefully, the important concept is, this electric motor will operate at variable speed, variable, or we can also call it adjustable speed. We can also call it adjustable speed. Now when this motor is operating as a variable or adjustable speed, what do you mean by that? The flow at the outlet can be controlled by changing or by adjusting the speed of this electric motor. Therefore, depends on the output only we are taking the power from utility system. Now, a straightforward without any equations, you can simply say that in case of second system, as we are consuming, means depends on our output requirement, we are consuming the power accordingly. Therefore, we can say second system is more efficient, isn't it? Second system is more efficient than the first system, because whatever the power you are taking irrespective of the outlet is always same, but most of the power is wasting in the form of a hydraulic losses at the throttle valve. Okay, therefore in the second system, by operating the electric motor as variable or adjustable speed, we can improve the efficiency of the overall system. Now the next question, how can we operate the electric motor as variable or adjustable speed machine? With the help of power electronic converter, or you can also call power electronic circuit. Therefore, the prerequisite for this particular drives topic to understand, we should have thorough knowledge of these power electronic converter circuits. I hope you have already gone through power electronic circuits modules through previous videos. Now, some of these circuits will be used in order to control this electric motor. So, throughout this drives topic, you should have two things in mind. So, what is electric motor? Basically, we will use either DC motor or induction motor. In case of DC systems, we will use DC motor. In case of AC systems, we will use induction motor. The more popularly used motors in the drives applications are induction motors rather than synchronous motors. Therefore, you just think about what power electronic circuits will give DC supply in order to power DC motor. So, basically we will have rectifier systems. If the supply is a single phase AC, we will use a single phase rectifier circuits, of course phase control rectifiers. And if the supply is a three phase, when you go for higher power applications, we will use a three phase rectifier circuits. And if the supply is a DC supply, unregulated DC, then you will have chopper circuits. So, all of these various power electronic circuits were explained in detail in our previous modules. If you have not gone through those modules, I will highly suggest you first you finish those modules and then only come to this drives topic. Okay. Suppose if it is a induction motor, nowadays popularly used power electronic circuits to control the induction motor drives or AC voltage regulators or inverter circuits. Okay, so these are the two systems that we will use to control the speed of electric motor like induction motors. Okay, therefore from this example, what we can say, the basic purpose of a drive, the basic purpose of an electric drive is to improve overall efficiency, to improve overall efficiency of the system, to improve overall efficiency of the system. Okay. So, the basic purpose of electric drive by using power electronic based converters is to improve the overall efficiency of the system. Okay. Now, we can have another simple mathematical way also just to convince this particular aspect. What is that? Now, here I took an application called a pump. Okay. Now, another popular load, fan, or let me write pumps, fans and compressors. Another load, blowers. Okay, for object exams these loads are important. Now, for all of these loads, what is the basic property? Load torque is proportional to square of the speed. Okay, load torque is proportional to square of the speed. Now, in these type of applications, if you employ variable speed drives, or let me call it motors also, variable speed drives, okay. The abbreviation is VSD or ASD, variable speed drives or adjustable speed drives, VSD or ASD. So in these type of systems, if you employ variable speed motors, then what will be the advantage? Say for example, in the first system, suppose let us say that this motor is operating at a speed of, let me take omega 1, okay. In the first system, the motor is operating at a speed of omega 1. Now in the second system, let us take that it is operating at a speed, which is half of the first system speed. First system is operating at a speed of omega 1. Now let us assume second system is operating at a speed of omega 1 by 2. So when you reduce the speed by half, now let us see what will happen with power consumption. Now say for example, when torque is proportional to square of the speed, we all know that what is the relationship between power, torque and speed? Power is equal to torque multiplied with speed, okay, speed in radian per second. Therefore, if T is proportional to square of the speed, then we can write in these applications, what all the applications we listed here, pumps, fans, compressors and blowers. In these applications, we can say that simply power is proportional to cube of the speed, okay, power is proportional to cube of the speed. Now, let us take the ratio of power consumption in second system and first system. In the second system, what is the speed? Omega 1 by 2. First system, the speed is omega 1. Therefore, what I can write down here, omega 2 divided by omega 1 whole cube. Therefore, we can prove here P2 is equal to P1 divided by 8. P1 divided by 8. This is very important conclusion. So, in a simple words, what we can say that, what all the applications we have listed out here, pumps, fans, compressors, blowers, in all these applications where torque is proportional to square of the speed, in such applications, whenever the speed is reduced by half, the power consumption is reduced by 8 times, okay. So that will be a great saving of electric power from the consumption point of view. So the basic purpose of electric drives, what we can say that it is to improve overall efficiency of the system. Next, let us look into what are the basic types of drives. Of course, different people used to classify in a different way, but from the application point of view, okay, so rather than the power electronic converters point of view, from the applications point of view, basically the drives can be classified into two categories. First one is positional drives or positional control. Drives are used to control the position of an object, okay. So let me write down briefly, this is to control position of an object. So basically, let me give you one practical example to understand what you mean by position control. Suppose there is a solar panel, okay. So when the power extraction from the solar panel will be maximum, it all depends on when the sun rays are falling on the solar panel, most of the sun rays falls on the solar panel, then the solar panel can extract maximum amount of power. So it all depends on the duration of a day. Say for example, solar panel is putting in one particular angle, but sun is at a different position. Like a panel is like facing like this, and sun is in the morning time it is somewhere, afternoon another time another angle, and evening like that. So the sun position will be varying. Am I right? So when the sun position is varying, if you somehow adjust the angle of, in other words, the position of the solar panel, it will always face the solar rays, therefore it can extract maximum amount of power. Thus the way how the solar panel angle can be adjusted, it is just like sunflower concept. If you see the sunflower, it will always try to face the movement of the sun. Okay, sun position from day to evening, it will vary, depends on the time. Therefore, whenever the sun is moving, so in the particular direction also, if you are able to adjust the angular position of this particular solar panel, we can extract the maximum amount of power from this solar panel concept. Okay, so whenever there is a motion in a particular object, of course physically daily human being cannot change the angular position of that particular object. Therefore definitely there will be an electric motor will be used. Okay, so this is one of the best example for positional system. Okay, so what I can write down here, example is sun tracking. Sun tracking in solar panels. Sun tracking in solar panels. In the similar way, if you take a wind turbine example, wind turbine will have generally 3 blades. So the maximum power can be produced from the wind turbine is at what angle the wind is hitting the blades. Okay, so when the blade is at particular direction and wind is blowing like this, it may not move at a more speed. So when wind is hitting like this, if you change the angle of the blade, then if it hits like this, then the blade will rotate at a much faster. So I hope you might study it in a power generation concept. The power produced from the wind turbine is proportional to cube of wind speed. Okay, therefore the wind blade, because you cannot control the speed of the wind, it is natural phenomena, right? So with respect to the wind angle of attack, if you change the angle of the blade, you can extract more power from the given wind turbine. Okay, so I can say here blade angle control, blade angle control in wind turbines. Blade angle control in wind turbines. This particular concept is also called pitch control. This particular concept is also called pitch control. So these are all the examples for position control. And another example is, probably you might aware of that. If you take a robo as an example, okay, robo is manufactured by assembling different types of levers, right? So the robo control is nothing but the angular position adjustment of this particular levers, right? Therefore I can say that angular control in robotics. Angular control in robotics. Okay, so in all of these applications, what type of electric motors are more preferable? Okay, So here, if you observe all of these applications, they need the torque. In other words, they need the shaft to change very precisely, okay, very accurately it has to change. Therefore, whatever the motor you are using, that motor should have smooth torque speed characteristics, okay. The motor should have smooth torque speed characteristics. So DC motor is best example for this particular characteristics. Therefore, in all of these applications, DC motors are best suitable. So, especially in our objective exam, these applications are very, very important, okay. Rather than the mathematics behind it, applications are very important. I am not saying that mathematics are not important. It is also important to justify the concepts, but applications in objective questions mostly will get application oriented questions. Now, the second basic type of drives are speed control. So, we need not to have specific examples, you might understand easily. The best speed control application daily we will use are fan type of controls, pump type of controls. In all of these things, let me write down here, to control speed of to control speed of an object, to control the speed of an object. So, what are the examples for this? Fans, what all the applications I have listed out earlier, pumps, pumps also the speed of the shaft we will control it, fans, pumps, compressors and blowers, okay. So, in these particular applications, excellent torque speed characteristics are not mandatory, okay, because even when you switch on the fan, of course, even 1 or 2 seconds delay, it's not a big deal. But in our earlier applications, very accurately it has to move. Therefore, excellent speed torque characteristics are not the primary requirements. Of course, it is good as much as possible the better torque speed characteristics, but very excellent characteristics are not the mandatory requirement. Therefore, in these particular applications, we can prefer induction motors. We can prefer induction motors, right? So, these are the basic types of electric motors. Now, let us discuss what is the important component or important aspect while designing the speed control of a particular system. Now, just a slight deviation I can have here. Say for example, if you recollect from control system object, because the drives involves one of the component I already mentioned, drive involves a control system also, okay. Therefore, if you look back into the control system concept, see what is the concept of a control system. Let me take a small example of a control system. What is the basic step or the first and foremost requirement to design any control system? We just need the physical modeling of a particular system, right? Say this is a reference input and this is present output or actual output, and you can say this is a plant, or you can say simply the process. And what about this one? When the plant or process is not having the required characteristics, by using some additional circuitry called controller or compensator, we will try to tune the plant to meet the required specifications. That is the basic philosophy of a control system, right? So when you are designing speed control of an electric motor, speed control of an electric motor. So let us take here DC motor, speed control of a DC motor. In this case, what could be the plant? In this case, what could be the plant of this system? That is basically a DC motor. Therefore, in the speed control application, what is required for us? There is a DC motor here. This is the plant, right? So for this DC motor, what could be the input? Obviously, that is a armature voltage. That is denoted with a VT, terminal voltage given to armature. Now the output will be either position, it is represented with a theta of S. In a speed control application, it can be represented with omega m of S. Okay. Therefore, when you are talking about speed control of a DC motor, what is the transfer function that is required for us? G of S is equal to theta of S divided by Vt of S. This is a position control transfer function or speed control omega m of S divided by Vt of S. If you recollect the control system concept, we have discussed all of these things, right? Now, let me look into that particular concept very briefly. Say for example, let us consider that there is a DC motor, okay? A DC motor circuit. Now, for this DC motor, I can take armature circuit like this. I can take armature circuit, and the terminal voltage given to this motor, you can say here that is a Vt. Terminal voltage given to the motor is a Vt. So this is armature resistance and armature inductance. In the armature circuit, you can also take back EMF here. Let me call it EB, okay? That is a EB. And the current flowing through this armature circuit, you can take it IA. Let us say IA of T, right? Now, the field winding, you can place it here 90 degree to the armature side, okay? The field winding is excited by separate excitation system. Let me take it separate excitation source VF. Now armature winding RF and LF. Now here a mechanical load will be coupled to this armature circuit, this can be represented with mechanical load property J and B, moment of inertia and coefficient of viscous friction. So here you can take, this is a TE, the speed, mechanical speed can be represented with the omega m, okay, and low torque can be taken opposite to TE. So basically this is a DC motor circuit representation, okay. Now this DC motor, how can we control it? So there are two aspects here. One is one converter. Let me say, we will talk about what all these converters. One converter is used to provide, in other words, to control this terminal voltage. Let me call that converter 1. Second converter will be used to provide field voltage. This is VF, okay. So this converter can be anything. I will give you the list of the various converters up to what power levels we can use it, okay. Now in order to control this particular aspect, if you see in the modeling point of view, how can we represent these equations? Now here we are all familiar with the electromagnetic torque produced in a DC motor can be expressed as function of field flux and armature current, okay. Therefore, I can write TE is proportional to field flux multiplied with armature current. In other words, electromagnetic torque can be expressed as TE is equal to KT, whereas a KT is a torque constant, multiplied with IA, okay, multiplied with IA. Or in terms of, okay, let me write down the all basic 4 equations first. Next, if you look into armature circuit, let me go back once again. So terminal voltage, how can we express it? Voltage drop across armature resistance, voltage drop across armature inductance plus back EMF, all together will give you terminal voltage given to the DC motor. Therefore, how can I write down here? VT is equal to RA multiplied with IA plus LA multiplied with DIA by DT plus EB. Let us consider all of these equations are in time domain and but back EMF of a DC motor can be expressed as the function of field flux and armature, field flux multiplied with the speed, where speed in radian per second. So I can say EB is equal to another proportionality constant KB multiplied with speed in radian per second, okay. Next, the electromechanical equation of a DC motor can be expressed as J into d omega m by dt plus B into omega m plus load torque is equal to TE, okay, is equal to TE. So these are all basic 4 equations that we can represent this DC motor. Let me say it is a separately excited DC motor, okay. Let us assume separately excited DC motor. What do you mean by separately excited machine? Field flux, you can assume it is to be constant, which is maintained constant by some external field source, field circuit, you can say. Now, what I can do here, let us convert all of these equations in the corresponding S domain by using Laplace transform. Okay, by using Laplace transform, convert all of these equations into S domain. Okay, so what you can write down here, TE of S is equal to KT multiplied with IA of S. Okay, after that RA plus SLA multiplied with IA of S is equal to VT of S. Okay, RA plus SLA multiplied with IA of S is equal to VT of S. You can simply rearrange the terms by taking Laplace transform. Okay, of course I am also assuming initial conditions to be 0. Next, back EMF EB of S is equal to KB into omega m of S. Okay, or you can also write down here KB into S into theta m of S, where theta m is the position. Why? Because speed is equal to, angular speed is equal to the rate of change of the position. In the linear velocity, you can say that rate of change of displacement. In angular velocity, rate of change of angular displacement. Okay, so if you take a Laplace transform on both sides, omega m is equal to S multiplied with theta m of S. Now here Js plus B multiplied with omega m of S is equal to, plus TL of S is equal to TE of S. Okay, TE of S. Therefore, what I can take here, what we can take, if you consider these 4 equations in a form of a diagram. So, how we can put it in a form of a diagram, that is, say for example here, this is VT, terminal voltage, one by RA plus SLA. Okay, and another point here is EB. So VT minus EB divided by RA plus SLA will give you armature current, that is IA of S. Second equation I put it here, and if you multiply IA of S with KT, then we will get torque, that is TE of S, and TE of S minus TL of S. Okay, TE of S minus TL of S divided by JS plus B. It will give you speed. Now that speed is multiplied with KB that speed is multiplied with kb will give you back EMF, okay. And say for example, if it is position control, then by placing one integrator we will get theta m of s. So the basically what I can say here, this is the mathematical representation of a DC motor, okay. So this is a basically mathematical representation of a DC motor. So from where we started here, this is the circuit, we are all familiar with this circuit. So this circuit we just put it in the form of what to say basic equations, mathematical equations, and from those equations we simply develop this block diagram. So what is the point that we need to understand here? Which circuit will provide this VT? Which circuit will provide this terminal voltage? What is the circuit here? This is a power electronic circuit, okay, or you can also say power electronic converter. Now for this power electronic converter, you will have some control aspect, okay, you will have some control. So this control system requires, see, you can say this is a control system. This control system requires actual values that need to be compared with the reference values. So what are the actual values? These are speed, okay. So the speed will be given input here and it will be compared with the reference inputs, okay. With the reference input, the actual speed will be given to this control system, so that if the actual speed is not as per the required speed or reference speed, then this control system will take corrective action and it will give suitable command to the power electronic circuit, okay. Accordingly, that power electronic circuit will be controlled. Now here the question is, what type of power electronic converters can be used in order to produce this terminal voltage to the armature circuit as well as field circuit. So for example, if the supply voltage is a AC voltage, then obviously you have to use rectifier circuits, depends on either single phase or three phase. And if it is a DC circuit, supply is a DC circuit, then you have to use chopper circuits, okay. Now I will give you the list of various circuits, what all the circuits that can be used, okay. Now let us write down here power electronic circuits that can provide DC supply to DC motor. Power electronic circuits that can supply or that can provide DC supply to DC motor. Now let me take here, let me give you the example here, a small table. Say for example, if DC supply okay, suppose if the source is AC, okay, let me take here AC source, source is a AC source. In that case, let me write like this: converter 1 and converter 2 power rating. So as I mentioned already in the beginning of this drives chapter, the prerequisite is power electronic circuits. Okay. Suppose, what is the converter 1 here? Converter 1 is a circuit that will provide terminal voltage to the armature side of the motor. Converter 2 is a circuit that will provide DC voltage to the field side. Okay. So what are the combinations here? Single phase, half wave, phase controlled rectifier. And here in the field side, single phase semi converter. Okay, single phase semi converter. So this type of combination can be used for the power ratings up to 0.5 kilowatt. Okay, so this table is very important for our objective exams. Now the second combination is in the armature side, single phase semi converter, field side also single phase semi converter. Okay, field side also single phase semi converter. This combination can be used up to power rating of 15 kilowatt. Okay. Next, in the armature side, single phase full converter, field side also single phase full converter. Okay, this combination can be used, again all single phase can be used up to power rating of 15 kilowatt. Next one, single phase dual converter, but here in the field side single phase full converter. This is also up to 15 kilowatt. So basically what I mean, single phase, these full converter circuits, whether it is in the field side or in the armature side, the maximum power capacity is up to 15 kilowatt, you can use it. Okay. Now suppose if the source is 3-phase AC source, in the armature side 3-phase half wave phase controlled rectifier, in the field side 3-phase semi converter. In this case, this combination can be used power ratings up to 40 kilowatt. Okay, up to 40 kilowatt. Next, another second combination in 3-phase, 3-phase semi-converter in both armature as well as field circuits. Armature as well as a field circuit. You can use power rating up to 115 kilowatt. Okay. Next, coming to second combination in the 3-phase. In both armature as well as a field, 3-phase full converter. This can be used up to 1500 kilowatt. Now the last arrangement, that is 3-phase dual converter in the armature side and 3-phase full converter in the field side. This combination can be used up to 2 megawatt. Okay. So this is combinations. So this table is very important, guys. In our objective exam, if at all question comes from these drives applications, this table is very important. Okay. So in the converter 1, converter 2 means armature side, this is the circuit, and the field side, this is the circuit. What could be power handling capacity of that particular drive application? Okay. Now there is another concept. As per the 4-quadrant application, let us look into these drives. So for example, based on quadrants of operation, based on quadrants of operation. So let me give you briefly what is each quadrant of operation. Say for example, so here from the converter point of view, V0, where V0 is given to the armature side of a DC motor. From the machine point of view, basically voltage will control the speed. So we will take a speed on y-axis. From the converter point of view, armature current on the x-axis, and from the machine point of view, torque, because torque current will control the torque of the machine. So here, so in the first quadrant, as both voltage and current are positive, you can say that power given to the motor is a positive. Okay. Therefore, this particular operation is called forward. Let me write down completely. Forward motoring. Okay. Forward motoring. And in this case, second quadrant of operation is called forward regenerative braking. And third quadrant of operation is called reverse motoring. Fourth quadrant of operation is called reverse regenerative braking. Reverse regenerative braking. Now let us look into what are all the circuits that will give you different types of operations here. This is another very important question. Now let us go with quadrant by quadrant. Now the first case, say for example, we want to have operation like this. This is I naught and this is a V naught, okay? And we would like to operate the machine in first quadrant of operation. So what is the first quadrant of operation? That is forward motoring. This is a forward motoring. So in the forward motoring of a drive application, what type of power electronic circuits are preferable? One, or let me write A. These are not options, guys. Okay, these are the different circuits. As I already used one there, I am using A here. If the source is AC source, then you can use either single phase or three phase half wave phase controlled rectifiers. So most of the cases, these circuits are more topic of discussion in the armature side rather than the field side. Okay. So three phase or single phase half wave phase controlled rectifier. Another combination can be single phase or three phase, single phase or three phase semi converter. Another possibility can be single phase or three phase full converter with firing angle less than 90 degree. And suppose if the source is DC supply, you can use type A chopper. So what is the circuit diagram for type A chopper? I will suggest you to go through choppers module, right? In that you can find out types of choppers based on the quadrant of operation. In that you can see the circuit diagram of type A chopper and all. Next, second possibility. This is I naught, y axis V naught. If you get a question like this, what type of power electronic circuits are preferable in order to operate the DC drive to get these quadrants of operation? In the first quadrant, it is forward motoring. Second quadrant, forward regenerative braking. So if you recollect the rectifier circuits, any rectifier circuit will give only positive output current because the basic devices used in rectifier circuits are unidirectional devices. Therefore, negative current is not possible. Okay. So what I can write down here, no rectifier circuit can have this feature. So rectifier circuit is not suitable for this particular application. Coming to chopper circuits type A plus type B, okay, these are together known as type C chopper, is together known as type C chopper, okay. So type C chopper is preferable in order to operate the drive in this particular mode. Now the third way we will get the question is like this. So in this case, what are the operations are required? Forward motoring and reverse regenerative braking. What are all the circuits that will have this feature? Coming to rectifiers, by using either single phase or three phase full converter. In case of chopper circuits, type D chopper. In case of chopper circuits, we can use type D chopper here to get this type of feature. Now another combination, that is a fourth one, all four quadrants of operation, I naught and V naught. Okay, so four quadrant operation can be possible by using single phase or three phase dual converter. Single phase or three phase dual converter. And from the chopper circuits, by using type E chopper, we can have this type of applications. Okay. So from these applications, what type of problems we can get in the objective questions? Say for example, what type of questions we will face? A particular converter circuit will be given in the question. It is driving the speed of a particular DC motor. Most of the cases it is a separately excited DC motor. Okay. So what type of questions we will get from this table? What type of ratings are preferable? And from this classification, if these quadrants of diagrams are given, what type of circuits you have to choose? Third way of questions are, circuit will be given to you. That means a DC motor is controlling from single phase full converter. It is operating at so and so firing angle. What could be the speed of the machine? So when that type of data is given, how to solve the problems? Okay, we'll see that. So basically, with only one equation, you should able to solve this problem. So what is that basic equation? You have to use, say for example, this is a power electronic circuit. Okay, This is a power electronic circuit. So this circuit can be anything. It can be a single phase full converter or type A chopper, type B chopper, depends on the application. So it is delivering power to, let us say, some DC motor, okay, some DC motor. Therefore, what is the balancing equation you have to use? Now follow very carefully here. It's a very simple concept. Don't scare about the drives problems. Terminal voltage, let me write order like this. Converter output voltage is equal to converter output voltage of the power electronic circuit is equal to terminal voltage of DC motor, okay. Of course, it will have some drop here plus back EMF. Therefore, what is the basic equation you should take? You should first start from this equation. What is V0? Output voltage of power electronic circuit. Say for example, if the power electronic circuit is single phase full converter, then V0 will be 2 Vm by pi cos alpha, okay. Suppose if the power electronic circuit is a single phase semi converter, then it will be Vm by pi into 1 plus cos alpha. So like that, V0 is the output voltage of a PEC, power electronic circuit. Vt is the terminal voltage of DC motor. How can you write down DC motor terminal voltage? In the steady state, RA into IA, where IA is average armature current. Most of the cases it will be mentioned that armature current is a ripple free or continuous conduction, plus back EMF, okay, where back EMF is expressed as KB into omega m. Electromagnetic torque can be expressed as KT multiplied with IA. So if you remember these basic outline how to do the problems, most of the drives questions you can do it, okay. So you just follow this procedure while doing problems, right. Now let us take few numerical examples.